This problem will illustrate the methodology required to integrate a problem that contains trigonometric functions in non-standard form where we have mixtures of cosecant and cotangent functions. Step 1 in the problem-solving methodology for integration is to determine whether this is a simple power or series of powers of x. Because transcendental functions are present, it is not going to be a power rule integral at first. Step 2 is to look for a function differential relationship. There are two functions which are present. Cosecant, which has cosecant 3x, which has derivative cosecant 3x times cotangent 3x times 3. The cotangent, of course, though, has only a power of 1 in that differential, not a power of 6. The function cotangent 3x has differential negative cosecant squared 3x times 3, not cosecant to the power of 4. Because we don't have a function differential, we then look for a standard form. This is not a standard form. It's not an integral that we find on the formula sheet. Step number 4. Is this a trigonometric integral, an integral with trigonometric functions in non-standard form? The answer is yes. This is not sines and cosines with an odd power. It is not sines and cosines where all the powers are even. It's not tangents and secants, but it is cosecants and cotangents. So we have to figure out how this is going to reduce, or how this is going to simplify so that we can actually solve it. Remember that the derivative of cosecant is related to negative cosecant times cotangent power 1. Cotangent power 6 is an even power and cannot be broken down into a series of even powers and a single power. So that's not going to work. But if we look at cotangent, derivative of cotangent is negative cosecant squared. Cosecant squared can be removed from an even power of 4. So that's the one that we should change. So remember, we have an identity that is available that is cotangent squared of an angle plus 1 equals cosecant squared of an angle. And so if I rewrite the cosecant power 4 into cosecant power 2 of 3x, cosecant power 2 of 3x times cotangent power 6 of 3x dx, one of those can be replaced. And the other cosecant squared will become the differential of all of the cotangents that will be left. So if I rewrite the cosecant squared as cotangent squared 3x plus 1, and I'm just going to rewrite the order here, cotangent to the 6th power 3x times cosecant squared of 3x dx. I've just rewritten the order so that it is obvious that the cosecant squared 3x dx is going to be part of the differential. If I multiply the brackets, what's inside the brackets, by the cotangent power 6, I end up with cotangent power 8 of 3x plus cotangent power 6 of 3x, all multiplied by cosecant squared 3x dx. And that is the entire method of using the trigonometric identity to rewrite the problem. We just inserted the trig identity into the correct place. What we have been left with, though, is now a series of powers of cotangent, all of which have the differential of cosecant power 2. So this is still not a simple power of x, but if we do the substitution, step 2, If I let u be cotangent 8x, the differential of cotangent 3x, the differential of cotangent 3x is negative cosecant squared 3x times the derivative of the argument, which is 3. And we have a dx when we move the dx from the left-hand side of the equation to the right to get a differential. This differential, negative cosecant squared 3x times 3 dx, is almost identical to the differential that we see in the problem. It will be entirely identical if I divide both sides by negative 3. And then I am left with positive cosecant squared of 3x dx, the exact differential which is in the problem. And if we do the substitution, instead of writing cotangent power 8 of 3x, that's going to become u to the power of 8. Instead of writing cotangent power 6 of 3x, that's going to become u to the power of 6. And cosecant squared 3x dx on the end is going to be replaced with du divided by negative 3. The divide by negative 3 constant can come outside of the integral, and so I place it in the denominator of the coefficient outside the integral. Now, after substitution, you start the problem over from the beginning. You ask yourself if this is a power of u, variable u, and it is. Both of them are powers of u and can be integrated directly. Integral of u to the power of 8 is u to the power of 9 over 9. And integral of u to the power of 6 is u to the power of 7 over 7. We have an integration constant plus c. And if we multiply this through, we end up with negative 4 over 27 is the coefficient on the first term. U to the power of 9, after integration, we can undo the substitution. This will be cotangent of 3x to the power of 9 minus 4/3 times 1 over 7 is minus 4 over 21. Cotangent of 3x to the power of 7 plus c. Until we know what this integration constant is, plus c, there's not an advantage of factoring this statement. If we know some boundary conditions and can solve for that integration constant c, then we might be able to factor out some common factors amongst all of them and allow us to simplify the equation. But otherwise, that is the solution to this question.